Okay, hello everyone and welcome to this video where we are going to review some concepts on convergence of random variables that are useful and important for applications in statistics. You have here an outline of what we are going to see. In this video we are going to start by discussing the difference between ordinary convergences of sequences of functions and convergences of random variables. We are going to continue with the distinct types of convergences. We will talk of one important case of convergence in probability or almost sure, which is the laws of large numbers, which are in the basis of statistics. We will comment about what happens when we transform converged sequences, in which cases they converge and in which way, and we will end with the central limit theorem. It is important to be aware that although we are going to go through all those topics, it is not a probability course, so we will not go in details or proof of all these results, which would require more time than we intend to have in this course for this topic. Okay. Let's start with a small recall. So we are talking about convergences and we are used to the idea of limits. So it is important to start by telling what's the use of the idea of a sequence or of a process. In general, we can use a sequence when we want to model something that evolves in time or in space. Usually, if we are not thinking of random variables, we will consider in a deterministic way. For instance, we can use a numerical sequence to describe the decay of a radioactive substance, such as we have here, where the quantity that remains after a certain time is proportional to the initial quantity times an exponential decay rate. Okay, so what does the limit tell us about this process? What is the quantity that we have left in the end? In this case, the limit would be 0. Okay, this should be an example of a numeric sequence, but for instance, we can also have sequences of functions. When we have a sequence of function, we have a kind of an evolution or a two-dimensional or 2 times n-dimensional processes, because we have something that evolves in space or in time by one side, but which is also a function. For instance, if we have the heating of a metal bar, we consider the heating of a metal bar, we have that F gives the temperature at the position X, but as the temperature, for instance, if the bar is not being heated, it is cooling, the temperature is decreasing following a certain equation in time. So we have a function succession instead of a numerical sequence. Okay, in that case, for instance, this function would converge to a function that would provide us with a uniform sequence when it is completely cooled down. Okay, now let's move. If we move on to sequences of random variables, when we have a sequence of random variables, we need to remember that a random variable is a mapping from the sample space to the real numbers. This means that we can say we have 2 levels of variation. By one side, we have that as n increases, each xn is a distinct mapping, because probably the form of the PDF will depend on n, and so we have distinct random variables. But by the other side, at each n, we have a distribution of values of x, which is the probability distribution of x. Okay, so we have again, in a similar way that we have, but not the same, in sequences of functions, we have a sequence that can be considered evolving in 2 ways. We can think of a variable that tends to a limit variable, but we can also think of a distribution the probability distribution that tends to a limit distribution. And this is not a trivial idea because it somehow allows us to classify the forms of distribution according to those two ideas. A useful concept for visualizing this idea of two dimensions is what we call a sequence path, a sample path. A sample path is the sequence of values associated to a given elementary outcome omega belonging to the sample space, okay? And the idea is that we can also talk of a realization of a sequence, but it's a word that is more associated with stochastic processes, which is also a good example for this. Okay, so the idea is that we can think of the sequence of random variables x1, xn, but we can also think of the sample path as x1 of omega, x2 of omega for a specific omega. If you look at this example, which is from the Convergence concepts package, it may be illustrated. For instance, we have here 10 dots which represent 10 elementary observations, and the values at each point, these are the values of these should be the values of x1 of omega 1, x1 of omega 2 until x1 of omega 10, and then x2 of omega 1, x2 of omega 2, and so on. So if we follow the same omega along n, or we could say a long time, we have the sample path. This is a good way to visualize what happens when we consider the evolution of a sequence of random variables. But we will not, we'll use it from time to time, but it is good. There is one package which is called Convergence Concepts, an R package, which is intended to illustrate the distinct types of convergence using examples of sample paths. However, the package is a bit old and uses a type of interface that I am not sure that if it's going to last. In any case, we will not be using it here. Okay, so again, when we are talking of convergence of random variables, we may want to consider two types of limits. We may want to consider a sequence of random variables, let's say x1, x2, xn, that tends to a limit random variable, and or we want to consider the probability distribution, which would be, for instance, the distribution sorry, I have to go back, not forward. Exactly. The probability distribution, which would be the values of all omegas at for every n, and then in that case we have that distribution tends to a limiting distribution. Okay, this idea is to somehow differentiate two big groups of convergences, those that refer to a sequence of variables that tends to a limiting variable, and that we require that they are in the same probability space. In that case, we have, for instance, when we talk of convergence of improbability or almost sure convergence, this is the type of convergence, or we have convergence of distribution functions, okay? When we have a sequence distribution that tends to a limit distribution. In that case, they random variables don't even need to belong to the same probability space. We can think of a sequence of discrete random variables that tend to a limiting continuous random variable. So the probability space is not the same. And we have, for instance, convergence in distribution. I have included here convergence in mean because at the end of the day, the mean is a way to summarize a distribution. Okay, so somehow we can put it here. Okay, let's now go into the details of each type of convergence. Let's start by convergence in probability. For this, remember that when we talked about for numeric sequences, the concept of limit is a familiar idea. When we want to define the limit, what we do is we say that as the sequence an has as limit when n tends to infinite by a, if we are able for each threshold that we want to imagine epsilon to find a value such that after this value of n, the difference between the limit and the sequence is below epsilon. Okay, this is the definition. Convergence in probability somehow relates to this idea, but we don't. It's less restrictive because we don't require that after a certain value n for a given threshold epsilon, the difference is smaller, but the probability that it is smaller tends to 0. Okay, so we say that the sequence converges in probability if the limit that the probability that the difference is above epsilon, so or that the difference is below epsilon tends to 0, or that if it's below tends to 1. Okay, so it's the same idea, the difference, but in probability. Okay, as we will see, this is a vague form of convergence because we can never be sure that it is not going to happen. The only thing we know is that what is not going to happen, that the difference is above the threshold. We only know that it is increasingly unlikely. Okay, I have put a series of examples, but I will not go in the detail with them. I have extracted some of them from this online book, which is Probability Statistics and Random Processes. So if you click here on the slides, you will go into the book and you can read what is before and after here. For instance, in that case, for instance, we have an example where we define a sequence of random variables by taking this a limiting variable x plus a sequence. Okay, so the sequence xn is the limiting variable plus the sequence yn, where yn is a sequence, if we look at it, which on average takes the value 1 divided by n, and whose variance is sigma squared divided by n. So in both cases, both the mean and the variance are decreasing. Okay, so in this case, and if you follow the example, which I will not go into detail, it can be proved that this probability ends up tending to 0. And what we do here is that we apply the Chebyshev inequality, which is one of the most common tools to prove Chebyshev inequality. So given that the probability tends to 0 as n tends to infinity, we conclude that this sequence converges in probability to x. Okay, which is the result we wanted to prove. Note this example is somehow arbitrary because it could be a bit difficult to think of we could think of many examples like error theory, where we have one perturbation, but and if the perturbation is asymptotically centered in 0, the original value is going to converge to the sequence is going to converge to the limit we want. Okay. In any case, one of the most common cases of convergence in probability is when the limit variable is a degenerate distribution. So it's a random variable which takes a unique variable with probability 1. Okay. In those cases, we talk of convergence in probability, but to a constant. And although it may seem a trivial example, it is important because it's one of the most common used or the most common found examples. Okay. For instance, the Wake, without going further, the Wake law of large numbers is a particular case of convergence in probability to a well-known constant, which is the sample, which is the population mean. I see here there is a typo. Okay. Okay, so for instance, we have here an example of a random variable with exponential distribution, which can be seen that this random variable tends to a degenerate variable of mean 0. Okay, this is immediate by the definition, because when we compute the probability that the difference is above 0, above epsilon, it is equivalent to find the probability that the variable is above 0, which is that limit, which is 0, given that it is an exponential distribution. Okay, so before we go into the next form of convergence, let's insist a bit on this idea of weakness. Okay, convergence in probability is very useful, but it's always, let's say, signaled for being not good enough. Okay, so the idea that the convergence is in probability, what it means, if these are, for instance, a certain number of simulated sample paths, we can see that as n increases, that it is unlikely that a given sample path is above or below the threshold. But as I said, we can never be sure that it is not going to happen. We will see another picture, because it is it's kind of saying that if we have a normal distribution centered at 0 with a small variance of 0.001, it is impossible that this distribution takes a value above 1000. No, it is very unlikely. The idea should be the same. How can we deal with it? Is there another form of convergence that allows us to deal with this problem? Yes, there is, and it is almost sure convergence. Okay, almost sure convergence is defined as we say that a sequence xn converges almost, a sequence of random variables xn converges almost sure to a random variable x if the probability that in the limit the sequence equals x is 1. So what it means is that the probability that for every omega, the probability of the event xn, or the sample path tends to xn, has probability 1. It is very common to define it in the opposite way, saying that the probability that this does not happen is 0. What is interesting is that it is not saying that there are no paths that can not reach xn omega to x omega. It simply says that the probability, or the probability or the measure of the set, of the probability of the set where this happens, is 0. And that's why we say that it always happens, because it happens with probability 1, or it always almost happens because it happens with probability 1, which is this, you can add this. Okay, so because the reason why we can say is this, because given that the set where this does not happen, where convergence does not happen, has probability 0, and this not, and a set of probability 0 will not affect the overall probability. Okay, so nearly every possible outcome will have xn close to x. Okay, so this does not happen in convergence in probability. In convergence in probability, we can never be sure for a given path that it will end up within the threshold. Okay, well, we will not, convergence almost sure is stronger, but to be honest, it is also stronger to work with it, to prove it. So many courses in large sample approximations, once they have commented it or not, they don't use it because of this difficulty. But it is, we will come back to it when we talk about the strong laws. It's important to know it is here, but we are not going to use it, or to use it almost never. Okay, so now let us talk of the weakest way of convergence, which is convergence in distribution. Why is it called the weakest way? Because we are not requiring here that a sequence of random variable converges to a given sequence, only that the sequence of associated distribution functions converge to a given distribution function. Okay, although it is a weak, less compelling requirement, it is very useful to know that the distribution has a certain limiting distribution. Okay, the definition of convergent distribution is if the sequence in the limit, the sequence of the distribution functions converge to the limiting distribution function at every point where this is continuous, at every continuity point. So this is something which is relatively easy to verify because it's an ordinary limit x set by the set of these continuity points. And for instance, although it is a weak form of convergence, as I said, it is very important in practice because, for instance, the central limit theorem is a well-known form of convergence in distribution. Okay, so for instance, we have here an example where we can study convergence in distribution if we have a sequence of random variables whose distribution function has this form, and we study the limit of this distribution. We can realize that the limit of this distribution is 1 minus e to minus x, and 1 minus e to minus x by the form of the expression is precisely the distribution function of an exponential random variable. What does this mean? It means that these variables, whatever its limiting distribution, converge in distribution to the exponential distribution, which is that the sequence of distribution has this limiting distribution. Okay, so that would be about the two forms of convergence of sequence of random variables to random variable, and one form of convergence in distribution. Let's talk of another also hard form of convergence, which is a convergence in mean. Okay, so as I said, a convergence in distribution is about the convergence of the cumulative distribution functions. Convergence in probability is on how likely it is that this likeliness tends to 0. Convergence, almost sure convergence, it is almost sure that they will converge except in the set of probability 0, but we never, in any of these forms of convergence, we are never quantifying how big is the difference while they are not converging. Okay, so if we introduce an idea of norm here that allows us to measure the distance between, or the value of the sequence at a certain value of n and the limiting variable, we may not only think of the convergence, but we may keep knowing how big is the distance, not only that it is likely more small as n increases. Okay, to do this, we introduce the idea of convergence in mean, which, as I said, can also be seen as a form of thinking on the distributions, because the mean is a summary of the distribution. So we can see it in the two ways. By one side, we can think of it we can think of it as as a way of convergence that accounts by the quantity in which they differ, and by the other side we can think of a way of convergence that focuses also on the distribution. Okay, so we say that a sequence convergence to xn convergence to a limiting random variable in the LP norm, or in mean, or informally, if in the limit of the mean value of the xn minus x to the p equals 0. Okay, but as I said, think if we realize that this is precisely the norm which provides a specific measure of distance between x and x, what we see is that this type of convergence is focused on the convergence of the distance. So we are always dealing with the distance which tends to 0 as n tends to infinity. Okay, a convergence in mean, as with the case of convergence of almost sure convergence, is a harder form of convergence that may be harder to prove depending on the cases. Okay, and to end with this first part, what we can give a look at is the different forms of convergence. Okay, And the relation between the different types of convergence may vary if the assumptions vary, but in general what we have is that when the sequence converges almost sure, it also is convergence in probability. The opposite is not necessarily true. When the sequence is convergence in R mean, it also converges in probability. We don't say anything about the relation between those two, and convergence in probability always implies convergence in distribution. Okay? Well, so it's a review of the different forms of convergence. In practice, we can think that when we need convergence in distribution, we will convergence of distribution functions, we focus in convergence in distribution, which is also called convergence in law. And when we need convergence of a sequence of random variables to a constant or to a variable, we would usually focus on convergence in probability, although if we can prove convergence, almost sure convergence, it will be better. Okay, so now let's talk about the laws of large numbers. Okay, so the laws of large numbers are, we could call it fundamental principles in statistics, which describe how the average of random variables behave. Okay, we have already seen many principles in statistics. We have seen the likelihood principle, the sufficiency principle, and usually the idea of those principles is, say, if we rely on sufficient statistics, or if we rely on a likelihood function or the likelihood ratio, we can obtain good results. The law of large numbers can be seen as a large numbers principle that says that if we rely on big averages, we are going to obtain good results. Okay, specifically, the laws of large numbers guarantee that under certain conditions, the average of large numbers of variables will converge to their expected value. Why am I writing here of a large number of distinctly related? Because although in our definitions we will use IID random variables, so let us assume we have a sum of independent and identically distributed random variables, this condition can be increasingly relaxed. So we have many laws of large numbers, for instance, that do not require that the mean is the same, that do not require they are completely independent, and so on. Okay, so although we are not going into detail, it is good to know that this is only the simplest version, as will happen also with the central limit theorem. Okay, so in that case, the Wake law of large numbers is stated with a familiar idea. So we have a sequence of IID random variables with mean mu and variance sigma. Then the limit of this, the probability that the sample mean, so the sequence of means minus mu is smaller than epsilon, is 1, which is equivalent to say that the sample mean converges in probability to the population mean. And this example, which I have extracted from another source, is interesting because what it shows us, the idea that I wanted to also to say when we discuss the convergence in probability, the probability is that the difference is above epsilon is increasingly small, but this does not mean that this may happen, may ever happen. Okay, so although we don't discuss here proofs, the Wake law of large numbers can be proved based on Chebyshev inequality, which is also the tool that we use when in many of the problems of convergences in probability, because we only need to realize that the probability, if we consider this a random variable focused on mu, we can even skip this. By Chebyshev inequality, this comes to be smaller than the variance divided by epsilon square, and the variance of the mean is sigma square divided by n square. Sigma square divided by n square, of course, tends to 0, so this probability as n tends to infinity tends to 0, which means that it converges in probability. Okay, as I said, this is only the basic law of large numbers, but we will keep with this right now. Okay, so what is the difference between the weak and the strong law? Well, the difference between the weak and the strong law is that under the same conditions that might also be relaxed, we have that instead of considering the limit of the probability that the limit is below 0 is 1. Not tends to 1. The probability that the limit is 1. Okay, so the law of large numbers tells us that the sample mean converges almost surely to the population mean. Okay, this is important. This is an important result, although I said that we will not discuss much about almost sure convergence, because essentially what allows us to use the large number principles in statistics, what allows us to say that the probability can be approximated by the long-term relative frequency is the strong law. Okay, so this is, if we only had convergence in probability, all these results would not necessarily be valid. Okay, so we can say that the strong law is crucial for the frequencies interpretation. Okay, it is this idea that allows us to do all those inferences that somehow substitute in the long term I'm trying not to say the estimator, but the function that converges in almost surely to the parameter, so the sample mean. Okay, if we only had the weak law, many of these results would not necessarily be valid, and we would have a much less strong basis for statistical inference. Okay, let's go ahead and let's talk now about what happens when we combine convergence sequence. Okay, if we combine convergence sequence, for instance, what happens? For instance, if we sum as convergence, not if we have exactly if we add convergence sequences as we did in the weak law, or what happens if we have a product, or we have a power, or any combination, any transformation of a sequence. Okay, notice that I am not saying convergence in probability in law, because the idea is does convergence of random variables convergence of random variables maintain under any transformation and any operation between random variables? The answer is that not necessarily, but many. And the results that we present are a subset of all the results available that show us precisely this, that under mild conditions we can add convergence sequences to obtain a convergence sequence in the same way or in a weaker way, and so on. So let's start by a known without name theorem, which is this result that says that if we have two sequences of random variables that converge in probability to certain two respective random variables, we can say that the sum of the sequences converges in probability to the sum of the limits. The product of the sequences converges in probability to the product of the limits, and if the probability that this variable Vn is 0 for all n above 1, then the quotient also converges in probability to the quotient. Okay, this can be proved directly but longly. Okay, and it is very useful in practice for many results, because in many situations we want to add up things. Okay, for instance, if we have a sequence of random variables, we can consider the sample mean or the sample variance. Okay, what we know is indeed the fact that the sample mean is converges in probability to the population mean is also I would say an example can be seen an example of a combination of random variables, but it is better not to see in this way. And also it can be shown that the sample variance converges in probability to the population variable variance, but it is not immediate because it is not a consequence of the version of the wake law of large numbers that we have seen, but of another law. In any case, if we have these two variables that converge in probability, we have that statistics such as the mean plus minus the sample variance will converge to the mean plus minus the population variance, or the quotient will converge to the improbability to that quotient, which will be very useful later in statistics. Okay. Now, in order to go into for a more general result is the continuous mapping theorem. The continuous mapping theorem tells us that under general conditions, if we have a continuous function and a sequence that converges in probability, the function of the convergent sequence converges in probability to the function of the limit of the convergent sequence. Okay, indeed, we could have omitted the previous theorem if we consider a multivariate version of this of the result, because in that case we could have function g of un vn to be the sum, the product or the quotient, and then we would only need that result. Okay, and talking, for instance, about the standard deviation, or sorry, the sample variance, in that case we can directly prove that the sampling variance converges in probability to the population variance, because if we decompose the formula for the sample variance in this well-known decomposition, we realize that this can be written in those terms, each of which converges in probability or to a known result, and in consequence we have that the sample variance converges in probability to the sample population. Okay, so and also we can have a bonus here, because given that convergence in probability, by the continuous mapping the standard deviation converges in probability to the standard, sorry, the sample standard deviation is known, or will converge to the population standard deviation. So to end up this series of convergence of transformer results, we state a theorem which has name, it is Lasche's theorem. It is similar to the previous one, but weaker, because what it tells us is that if we have a sequence that converges in distribution to another one, and a sequence that converges in probability to another one, then the same operations that we saw still are valid, but the convergence of the same operations, but in distribution. So in that case, let's say that the weakest form of distribution is the one that is kept. Okay, this theorem is very useful, as we will see for large sample approximations, but we keep this for another video. Okay, so now let's move on to the last result, which is the central limit theorem. Okay, the central limit theorem, as is known, is a crucial result. It's and indeed it's an intriguing result, because it's kind of a silent call of sums of random variables onto the normal distribution. Okay, what it tells us, again, in many versions, is that the limit distribution of the standardized, not of the, it doesn't tell, remember that, not to cite it, not to say it badly, it doesn't say that the sample mean is normal in the limit as n tends to infinity or as n is bigger than to 30. We will see the definition. What it tells us is that as n tends to infinity, the standardized sample mean, so the sample mean divided by the centered on the population mean divided by the standard deviation of the sample mean, converges in distribution to the normal distribution. This is, as I said, the weakest form of convergence, but the number of applications of the central theorem, limit theorem, is so big in statistics that, of course, it is very important. This is the definition, as I was saying, is if we have a sequence of IID random variables, this can also be relaxed, we will not see, and whose moment generating functions exist, so at least we need that these moment generating functions exist, then if the variance is mu, the mean is mu, the variance is sigma, and is finite, as I said, the standardized distribution of the sample mean tends to a normal 0-1 distribution. Okay? Well, this is, as I said, an important result that has a big number of applications. As a short example, for instance, we can say here that this applies to both if we have a Bernoulli random variable simply by the terms of the theorem, or if we have some binomial random variable which can be seen as a sum of Bernoulli random variables. In both cases, directly or by considering the binomial sum of Bernoulli random variables, the central limit theorem establishes that we can approximate the standardized distribution by a normal 0-1. And that's all for this first video. We have seen a quick review from the idea of convergence, the types of convergence, how to transform convergence sequences, the laws of large numbers, which are important, and the central limit theorem. In a later video, we will see some results that we can globally put in a bag that we call large sample approximations, that of course relies on this one. Here we have some references, like, as I said, those two papers on convergence, and also this is a link to the book Introduction to Probability, and it's not that name. the book is called Probability, Statistics and Random Processes, but here you find a chapter on convergences with all these results, many examples, and solved problems. Okay, I hope you found it interesting, and that's all for now.